Thanks so much. I can take it from here. All right. Hi, everyone. Good afternoon from Palo Alto, California. It's exciting to be here, and thanks for sticking it out, I'm assuming, towards the tail end of the conference. I'm Manasi. I'm the founder and CEO of Verta, and I'm thrilled to be speaking with everyone today about a topic that I spend a lot of time working on, which is what is MLOps, DataOps, and DevOps. In the next 30 to 35 minutes, I'm hoping to give everyone a quick overview of what these terms mean, how they apply to us as practitioners in data science and machine learning, and most importantly, what does that mean for you? How will it impact your day-to-day, and how can you impact your organization to best leverage all of these areas? So with that, let me get started. I will turn off my video so that you guys can see the screen a bit better, and then I'll be back around Q&A time, and looking forward to seeing you all then. All right, so let's move on. Cool, a bit about me and why I'm here speaking with you today. So my background is technical, did my PhD in computer science at MIT, worked on some of the first model management systems, in particular built an open source system called ModelDB, which then led to what is now called the experiment management space. So it's very gratifying to see that. And then started Verta, which really productizes some of the ideas that we developed at MIT. In addition, I've had the chance to do hands-on data science and ML at Twitter, Google, and Facebook. And so I've seen what scalable ML looks like. At Verta, we built what might be called an MLOps platform, and I'm going to define that in a few slides. But what we do is we provide a platform for ML model delivery, operations, and management. So we take care of everything that happens after a model has been trained, and we really specialize in doing it at scale and a data science friendly way. We're one of the sponsors of ODSC, so you might have seen some of our ads, I guess, or might have visited the booth. If you haven't, check it out. But here's what I will cover today. I'll start off with a quick overview of building intelligent applications, what it takes to actually do that. We'll go through the key highlights on DevOps, MLOps, DataOps, and then finally spend a lot of time on what it means day-to-day for data scientists, ML engineers like you and me as we're doing our jobs. So we're all here, to set the stage a bit, we're all here because we believe one thing, and that is the future is intelligent. So in the next 10 years, effectively every piece of software or hardware we're going to interact with is going to have intelligence built in. It's already available in YouTube. It's available in our emails, which really write and finish our sentences for us. It's in the Roombas and robots we have in our houses. It might be smart kitchen appliances, bassinets. It could be the wind turbines that are now operating in sort of auto mode. Overall, every software component in the future is going to be intelligent. And as a community, that is what we're really working towards. But as you probably know, there is a lot that goes into building an intelligent application. And I've picked an example of an intelligent application to make the case here. So consider building a perception system for a self-driving car. This is a picture from Tesla that's talking about how they use their sensors and cameras in order to figure out if there are obstacles on the road, what the lane markings look like, so on and so forth. On the left here, I'm showing everything that's involved, a simplified view, mind you, of what it takes to build and deploy a perception system. So it vaguely goes like this. You get data from the cars you have on the street. You build one or more models for perception. You spend a lot of time doing that, in fact. You run the models on different test sets. You might have a golden data set. You might want to test it in low light conditions, conditions when there has been rain, there's snow on the street, so on. Once you do that, you want to run the models and all the surrounding code in a driving simulator, because the first time you test these systems should not be directly on the road. There needs to be a more confined environment, and that's our driving simulator. Then, assuming that you pass the tests, you're going to go off, package the models to run on the car. You'll then deploy them into the said car. And once deployed, the models will make predictions as you go along. They're going to detect your obstacles, they're going to detect pedestrians, so on and so forth. And then a big part of the system also captures results from these predictions back. And these results then go and inform the data. So you would look at, where is my model making incorrect predictions? Maybe you want to collect more data and then ultimately improve the model. So number 9 then goes back to 1. Now, there's a few things I would like to highlight here. Building an intelligent application is way more than building a model. It's also way more than just working on the data. It's this really intricate mixture of what we call the model, data, and code triad. And every intelligent application stands on these 3 legs or pillars. And each one of these actually has a lot going into it. For example, if you're talking about data, you have offline features, you have online features, there's labels, maybe there's someone hand labeling your data. You're collecting ground truth by some mechanism, and then there's raw data that gets ETL'd into a format that works for your model. So that's just on the data side. Let's look at the model side. We're training the model, we're doing hyperparameter optimization, we're doing testing, robustness, validation, et cetera. Fairness, explainability might be a concern. And then model serving, which is actually the way that all the research that we're doing actually matters. If the model gets served, great. If the model doesn't get served, it doesn't make its way to production, and that's not terribly useful. A big part of these applications is also the code, and this includes the business logic. So this might be in the perception system, you're taking inputs about what obstacles are on the road and making decisions about where to go next, how to change your navigation. It could be code that's calling the model. So there's code that actually calls the perception model, receives its output, and then either calls another model or takes a decision. There are code that is just making calls to other data systems. Maybe it's a database, maybe it's a cache, whatever is appropriate. And so if you look at any intelligent application, Siri, your email, a writing service, you name it, you can actually break it down into these component parts. And the reason why we like to frame it in these 3 pieces is the following. The 3 areas that I just mentioned on DevOps, MLOps, and DataOps are effectively the operations components that keep these 3 pillars working as efficiently as possible. So DevOps is going to make sure your code that is outside of the realm of models is working as expected and is interacting with models properly. Your data is making sure that your data is high quality. Models also similar. We're going to go into the details of what each one of these things means, how are they different from each other. But at a first pass, this is what DevOps, MLOps, and DataOps is. And as you can see, all 3 are necessary for you to build really good intelligent products. So with that, let's dive in and let's see what each of these components of ops means and what tools are used there. So let's start with DevOps, because this is really where it all started. MLOps and DataOps really pick up the practices of DevOps and apply them in very different settings. So here's a brief view of DevOps. It really stemmed from the fact that software development was waterfall for the longest time. It's like you first plan, then you build, you test, and then you ship, as opposed to what happened next was agile, where you're working in tighter sprints, you're constantly delivering, and so you get a chance to optimize your product as you go along. About the 2010s, 2009s, there was this big movement to combine what is software development and operations. That became DevOps. A really major talk around that time was how Flickr did 10 plus deploys a day, and that was unheard of. On the backs of those developments came the open source tools that I hope some people in the audience at least use in terms of Jenkins, Chef, things that we've been using for DevOps for a while. And so ever since that time, the best software engineering organizations have been using DevOps practices in order to ship faster. So this is another way to look at DevOps. And if someone asks you, like, what is the point of DevOps? I would answer it as it's the processes and the tools we use to ship high quality software faster. And this is the very popular DevOps loop that people use. It goes from the planning stages to the creation, the testing or verification, packaging, release, configuration, monitoring, and then back. As you can tell, there's a whole host of tools that have been developed in the last 2 decades effectively to support what is the DevOps lifecycle. And the goal of DevOps is not only to provide tools for individual steps, for example, version control with Git, but also to provide workflow automation. This would be something like Jenkins that's helping you build in continuous integration, continuous testing, and so help you to make sure anything that you are shipping is of high quality. So that's DevOps. Hopefully folks are on board with the definition here. Feel free to throw in any questions that you might have as we go along. But those are the key principles and approaches that have now been applied across ML and data, and that's where we'll go next. So we looked at DevOps. Let's look at MLOps, because that's probably where most people in the audience work or are looking to learn more about. So this is our view, so the Verta view of the AI/ML model lifecycle. Should be fairly straightforward. You're doing data prep, you're doing training, and you're validating, you're deploying, operating, and then monitoring. And each one of these steps in turn has a lot of things going on there. There might be feature engineering, automated pipelines that get you the data. Maybe there's labeling and cleaning also going on there. With training, you've got your actual model training, getting the resources to support that, GPUs, hyperopt, orchestrating the retrainings. You might have testing, you might have robustness checks, explainability, fairness. When you get to deploy, you've got packaging. How do you roll out a model most effectively? CI/CD integration. With operations, you have everything that comes in to make sure that your model keeps working and it's not just deployed and then no one knows what's going on with it. So this includes things like auto scaling. Are you meeting SLA expectations? Is the resource utilization as expected? High availability. So what happens if some of your model replicas die? Are you able to spin up new ones? Things like that. And then monitoring here, I'm focusing more on the data monitoring. There's also a systems monitoring aspect to it. You care about collecting ground truth, drift detection, model quality, outliers, anomalies, so on and so forth. So this is a quick overview of everything that needs to be performed in order to have a production model. If you're not putting things into prod, you can probably do away with a lot of these, but the most interesting things happen when someone uses your model. And so similar to DevOps, what MLOps does is it makes this journey through the life cycle way faster and efficient. What that means is MLOps provides you tools for these individual steps, and it provides some amount of workflow automation. Looking at the complexity of this life cycle, you're going to find that there isn't one silver bullet, one all-inclusive MLOps platform. You're going to find tools that help you in specific pieces of the ML lifecycle. They might do one or more, they might work well together. And then hopefully some of them help you figure out how to go from one step to the other via automation. And so if you're looking at, hey, we need to get an MLOps platform, you're likely going to buy a set of tools and you're going to make them work together. And what you would want to optimize for is this set of tools helping me automate some of the manual pieces? Are they bringing safety to this process? And are they helping me go faster? So in a bit, I'll also talk about how DevOps is different from MLOps, but for now, I'll leave it there with what is MLOps, and then we'll take a brief look at what DevOps is next. Sorry, what DataOps is next. All right, so we've covered off the model components and the code components. The last component is the data. And for anyone who's worked in data science, it's one half of the title right there. We've seen very well-defined life cycles for the other two components that we've discussed. DataOps right now, I would say there's a lot of definition happening in this field. And so I think a good way of characterizing it that has been covered in this blog post that I've linked to below is that DataOps is a combination of data engineering, it's data quality, ensuring high quality, data security, and data integration. And so as before with DevOps and MLOps, what a DataOps platform or DataOps engineer is doing is supporting the tools that help perform one of these activities and helping to build workflows, for example, that take data from Airflow, maybe do some transformation in it, and then make it available for a BI tool. So that's the kind of automation that is involved in DataOps. As you might imagine, the skill set and the tools required for DataOps are quite different from the ones that you might need in MLOps and DevOps. So just in terms of what terms are alike and what terms aren't, DataOps tends to be quite separate and different from what is DevOps and MLOps. So before we get to the section of what does this mean for day-to-day work, let's talk about how MLOps and DevOps are different. As I mentioned, with DataOps, the tools that you work with are very, very different. You might be administering databases, you might be working with caches, you're writing a lot of SQL queries, you might be dealing with Airflow or Spark, very different ecosystem. MLOps ends up reusing a lot of DevOps tools and principles, but because of the domain, it actually ends up looking very different. For example, there's very few DevOps engineers that we've come across who have been able to make the transition, for example, to MLOps. MLOps engineers seem to come from a background in ML and data science or software engineer who has picked up ML. And to summarize the differences, they're really just two. One is the domain and activities are very different. Model training and testing looks very different from code build as well as test. What does a test case even mean for a model? How do you test the data that's going into the model? Similarly, model monitoring and what is APM or application performance monitoring has wildly different requirements. One of them is looking at CPU utilization, your throughput, your latency. Model monitoring is looking at what is your model quality, what is your data quality, and triggering alerts based on it. And then the people that you are building for or you are serving are very different. The primary users are data scientists, as you might expect in MLOps, and software developers in DevOps. And so the tools necessarily need to look and feel different. And then finally, MLOps needs a much tighter integration with data than traditional DevOps has historically. But MLOps is not DataOps given all of the unique constraints there. So hopefully that makes sense. To summarize, what we're talking about is when you're building intelligent applications, there's these three pillars: model, data, and code, and therefore you need ops for each one of these pillars in order to make sure they're working as effectively as possible. So that's a quick overview. I think the key part that all of us are probably wondering about is, all right, so what does it mean for me? I might be a data scientist, I might be a manager of data scientists, I might be a data engineer. What are the boundaries and what can I expect to do in my job? So I'll highlight three things here on what does this new configuration for developing applications mean. The first one has to do with structuring teams, and perhaps some folks here already have some experience with this. But what we're finding is that there's two very popular ways to structure application development teams when building intelligent products. The first one is pod structures, where you have a data scientist, a data engineer, and an application software engineer working together very closely to deliver an intelligent feature or an intelligent product. This works really well because it helps you iterate very, very fast. The challenge here is that the pods tend to get siloed, and so sharing knowledge between the pods becomes that much harder. On the other hand, we have what's called the Center of Excellence structure, or COE structure. Here, all the data science teams fall under one umbrella. Maybe there's one manager or VP that's managing them, and they get assigned to different products depending on requirements. Similarly, there might be a data engineering COE with a set of data engineers reporting up to the same manager, and these resources get pooled across products. Now, the advantage of having a COE is that you can share knowledge very easily, but it can lead to slower iteration cycles because folks are not dedicated to a particular product. Which structure works for organizations really depends on how the rest of the org is structured and reporting relationships, but here's two typical ways in which we've seen intelligent app teams being structured, so something to keep in mind. This also impacts infrastructure. What we've seen over and over again is when you're dealing with a complex product like an intelligent app, getting dedicated infrastructure teams for each one of these pillars is crucial. For example, we've historically had DevOps teams that support application or product services. So this is your regular software engineering teams who are supported by DevOps, and they're producing different kinds of application services. For data services, we have, to a degree, had data infrastructure. This took the form of database admins. These days, increasingly, it is someone who manages your Airflow installation, your Spark clusters. Maybe there's a feature store in there that you're also working with. And the data infra layer is really managing those tools, filling in the gaps wherever necessary, and giving a smooth operational experience for the data engineers who are working on the data and making sure that data services continue to operate as expected. And then finally, we have the model services. The model services, think of them as models that other teams will use. So you might have a credit recommendation model that might be used elsewhere. You might have a spam model that also could be reused. You might have a model that just takes a piece of text and then embeds it, and someone else could be using those embeddings downstream. So this could take a variety of different flavors. Again, what we've seen is having even a small but dedicated ML infra team goes a long way, because if you remember the AI ML lifecycle, there's a whole host of things that need to be done just to help the data scientists do their job. And so a couple of dedicated engineers here hooked up with whatever open source cloud vendor, commercial vendor products, they can actually make a lot of headway here. So something to consider if you are in this area and you're in data science, make sure you actually have some dedicated infrastructure people, and you have ways to communicate with both people whose products you're consuming, like the data services, or people who are consuming your products, which are often the application services team. So that's a bit on teams. Next, let's talk briefly about tools. Now, there is a whole host of tools available in the MLOps space, and you can pick and choose whichever one makes most sense for you and so on. The things that make some tools exceptionally useful are the following, and these all stem from the fact that you're working in a highly interdependent situation where collaboration across model, code, and data teams is really critical. So the ability to discover things, for a data science team to discover what data exists or what features exist, is extremely important. Similarly, a way for your application teams to discover what models exist, what versions are the latest, is super critical. And with that, documentation. How do I use this really fancy model that has been built? When is it appropriate for me to use it? Is it only for certain kinds of users? Is it only in certain applications? There's also an aspect of governance here that comes in, which relates to the next point, which is you want to build tools, or you want to buy tools that really encourage safety. Because the code team, which is using your models, is not the same as the modeling team, we often see a lot of off-label usage for models. So there might be a model that, say, predicts gender of a user based on their metadata, and that might be okay in certain applications. But if you're doing, say, any financial recommendations or applications, that's a complete no-no. However, for someone who's just building an application, they might not be aware of it, and they might just use it because it's available and it seems to give them better results. So baking in safety or controls on who can use what models and also data turns out to be pretty important. I think most people here probably have been bitten by undeclared dependencies and things breaking due to unexpected changes. Often it is something upstream on the data side breaks, so data service breaks, and so the model breaks, and so the application breaks. As you might imagine, debugging these intelligent apps becomes extremely hard because you need to figure out which of the 3 pillars the bug is in, track down the right people, hopefully they have enough logging, and then try to piece together what went on. So safety is something that you want to emphasize and also make sure you're selecting for. And then we found that self-service really wins. So an example of this is your ML team should be empowered enough to take the models from training to production themselves without having to ask the code team, for example, to help them run their models. That's why your ML infra exists. They should be able to take you from 0 to 1 very, very quickly. Similarly for your feature stores as well. The point of an ML engineer is not that they take your code and then turn it into SQL queries. The more that you can make your data scientist self-serve, the faster they're going to be able to build products that are ready to be put into production. So consider self-service. And then finally, know when you want to build by. There are a lot of tools in the space available, and focusing on business specific needs. So is it more important for your team to build the best models? Is it more important for your team to, own your Airflow cluster? Is it more important for you to own your application development? That's a business call, but that's something to be considered when deciding whether you want to build something in-house. And there's compared to 2015 or so, when a lot of these ideas first came onto the scene, we've come a long way. So that's a bit about tools. I'm happy to answer questions during Q&A about tools because there's quite a spread there. So let's wrap up with ownership, which is, I would say, the last key piece here, which is who has ownership and who decides KPIs. And something I find really helpful to remember is we're all working in companies or maybe academic labs. Especially in companies, the goal is to build the best product to bring in better revenue. So if that means that you need a model that might be only somewhat accurate but fails in really predictable ways, then that's the KPI that you want to optimize for. The KPI is not the best model that fails in unknown ways. And so depending on whether you're, for example, in healthcare, that matters a lot. You want to know when your model is going to fail. If you are, say, in a recommendation system on an e-commerce website, these model failures are probably not that expensive and you can optimize for overall accuracy of your model. So in this case, what we found very effective, or the best, I would say, product teams do this well, is that the product owners or PMs drive the KPIs. So it's usually a combination of, is the product meeting user expectations, some delight, revenues, user complaints, and then the pillars really derive their KPIs or key metrics from this. So for models, we've seen effective metrics be the number of model iterations shipped, model quality in production, is the model meeting performance SLAs. And of course, there's always a support for these services and how well can other people use the model. For data, similarly, it's frequency of data refreshes. Is it every day? Is it every month? Are there data quality issues? Can I access the data as quickly as required? Are there different modalities of accessing the data? And then code, as we know, we've been building and writing code for a while. So number of releases, number of bug fixes, number of new bugs introduced, whatever it might be, number of features that have shipped. But the key point here is to drive all of these based on the product KPIs and to focus on the agile principle, which is how quickly are you moving and how many deploys are you doing. So with that, we covered a bunch of ground today, and I'd like to leave you with a few key ideas that are hopefully useful. The first one is when you're thinking about an intelligent application, remember that it stands on 3 legs. You got your model, you got your data, and your code. And if one of them is broken, product is not going to work. MLOps, DevOps, and DataOps, since they work in such different domains, are distinct, and you will need distinct people handling them. And if you try to shoehorn the same person into multiple areas, it's going to be pretty challenging. But all of these optimize for the same thing, which is iteration speed. How many times are you releasing? How many iterations are you going through? And maintaining high quality. This could be via testing. If it's a data product, then knowing how many errors are in the data, so on and so forth. Team structures and tools can either help build this application and help collaboration, or they can bog you down, and so choose wisely. And ultimately, it is the product owners who should drive KPIs. And if you're working on a data science team or a data engineering team, know what metrics your team is looking to optimize for the business so that you guys can invest your resources in the right spot. So with that, I would love to open it up for questions. We, I believe, have 10 to 15 minutes for questions. Happy to get into details of anything I spoke about. And yeah, thank you for your time.
Thank you, Manasi. There's some questions or requests for the links in the chat on the live.dec.com. If you can take a look there.
Yep, absolutely. I believe we're going to be sharing slides anyway, so folks should be able to find links to the slides, and the blog post. APM is, yeah, application performance management. For MLflow and Kubeflow, so there's a ton of tools in the space, and MLflow and Kubeflow are 2 of them. MLflow actually came from my PhD thesis called ModelDB, so that's an experiment management system. Kubeflow is much more of a workflow orchestrator for ML, and so it's going to do some of the things that Kubeflow in particular is going to do some of the things we talked about, which was training, also hyperparameter optimization. It increasingly, I think there's also some integrations into feature stores. So it's trying to include as many parts of the lifecycle as possible. All of these are work in progress, so you're going to find that new features get added all the time. Got it. Which open source would be useful for MLOps? I can put in a different link in the chat right now too. So I'd given a talk on robust open source MLOps, and you can actually combine a variety of open source tools to do that. I will put this one. This one is an example using Jenkins, using Docker, and Prometheus in order to do the operation side, so everything that comes on after training. I think if you're looking for something that does training well, then I think something like Kubeflow is probably adequate for your needs. Cool. Other questions?
Yeah, I didn't see anyone coming, but probably someone is still typing in. Just a small reminder, while someone maybe needs a minute or two for the question to type. There will be short survey in the end of the session. Please take a moment of your time to fill it in. And other than that, if you would like to reach out to Manasi, you can do it still here on the platform. The chat will be open throughout the conference and afterwards even. So if something was shared here, it will be saved. So we can come back, or as well, there will be the prerequisite link that you can find the slides from this specific session. Just in case, I will share as well here if you will need us. But that's probably the main points. Let's see if there will be any additional questions coming, and if not, yeah. Oh, there is about the questions once again. Yeah, about the slides. That will be slide shared. I will share actually here the prerequisite link. So there's supposed to be the slides.
Great.
That was the only additional question that were coming. Nothing else.